So we're going to continue on our understanding of the electron arrangements of atoms. Now, in the previous video, we looked at electron configuration, orbital diagrams, the quantum numbers, and how we can determine each of these. What we're going to look at now is the trends in the periodic table, because atoms have sizes. We usually describe the size of an atom. We think about mass, but the size of an atom, if I want to say how big something is, I want to know how much volume it occupies. And our measurement we usually use for volume is radius. Now, we know the radius of a sphere is 4/3 pi r cubed. So r is going to give us a good measure of what volume an atom is going to occupy. So we're just going to look at atomic radii, and generally that is measured by taking two atoms and taking a look at how far apart their nuclei are and dividing that by 2. So that's atomic radius. We're also going to look at something called ionization energy and electron affinity. Okay. Now there's a lot of, I just talked about these, here they are listed. The covalent radii is what I was talking about. But as we go down a group, we add energy levels. So as we go down in the periodic table, it's a little easier to see. As I add layers of electrons, they're going to get bigger. But what happens as I go to the right on the periodic table? Okay, as I go to the right, something else happens. Okay, I would expect that as I add more electrons, they're going to get bigger, but that's not what happens, because in addition to adding electrons, I am also adding protons in the nucleus. And because I have the same number of energy levels, that increased charge in the nucleus has a greater attraction for the electrons. Now, if we take the outer electrons and the nucleus, and in between there may be some shells of electrons, those are called shielding electrons, okay? The effective nuclear charge is generally calculated by taking the number of shielding electrons and subtracting that from the number of protons that are present. There are other ways of calculating the effective nuclear charge that are a little bit more accurate, but for this class, we're just going to keep it simple. We're just going to take the shielding electrons and subtract it from the total number of protons. Now, in the case of hydrogen, there's only one electron and one proton. So the nuclear charge is 1, and there's no shielding electrons. So the effective nuclear charge is also 1, okay? As we increase the effective nuclear charge, the number of shells doesn't increase, but the positive charge of the nucleus does. So as we go from left to right on the periodic table, the atoms get smaller. The radius of the atoms decreases as we go to the right. And that's really important for us to understand. So here we have an example. This table shows relative sizes. And as you can see, as you go to the right, they get smaller. Now, yes, there are occasional exceptions that as you go to the right, one might be slightly bigger than the others, but almost always, but not always, as you go to the right, they get smaller. That's why it's called a trend instead of a rule, okay? And that is because of the effective nuclear charge. We can take a look at the atomic radii. Notice every time we add another shell, I have a great jump in the radius of that. And as I go to the right in the periodic table in the same period, my radius decreases generally. And that happens all the way through, okay? We can also measure the radius of an ion. Now, think about this, okay? If I have a cation, I have removed an electron, but I have the same number of protons. So I have exactly the same positive charge, but less negative charge. So I have decreased the electron repulsion, but not decreased the charge. So cations are smaller than the atoms from which they are formed. Now, the same thing is going to happen when I have an anion. If I add an electron, I'm going to increase the electron repulsion without increasing the nuclear charge. So an anion is always larger than the atom from which it's derived. okay? A couple examples here. Aluminum, see, it loses 3 electrons. It becomes much, much smaller when it becomes an ion. Sulfur, as it gains 2 electrons, it becomes significantly larger. And these are just examples, okay? Now, I talked in the last one about isoelectronic species. These are species where the ions have the same number of electrons and a different number of neutrons. Now, if I have the same number of electrons, the smallest one is going to be the one with the most protons in the nucleus. The largest one is going to be the one with the least protons in the nucleus. So if I look at this first row here, nitrogen only has 7 protons in the nucleus. If I go all the way over to aluminum, it has 13 protons in the nucleus. So that charge, that 13 positive charge in the nucleus of the aluminum, is going to cause it to attract those electrons to a much smaller size. Okay, so the greater the nuclear charge, the smaller the radius is. Okay, if they're isoelectronic, the smaller one is the one with the most protons. Now, I've said that redundantly over and over again. It must be important. Okay. We also need to identify something called ionization energy. Now, we can't just knock an electron away from an atom. There has to be some energy involved in it. And the amount of energy required to remove an electron from an atom is called its ionization energy. Now, very specifically, it's defined by removing an electron from the gaseous atom in its ground state. And that's called the first ionization energy. Now, if I take that ion and knock another electron away from there, that's the second ionization energy. And as I knock successive electrons off, I always have an increase. The second ionization energy for an atom is always higher than the first ionization energy. But there's also some trends in ionization energy as we go across the periodic table. And I want to go ahead and take a look at those just a little bit, okay? We're going to go ahead and stop the sharing here, and we're going to write on the board a little bit again. Okay, now there are 4 factors that affect ionization energy, and a couple of them are really simple. We already talked about the effective nuclear charge, okay, and that is why the atoms get smaller as you go to the right. But as I increase the number of protons in the nucleus, the effective nuclear charge increases as long as I don't add more shielding electrons. But this increase in the effective nuclear charge makes it harder to remove an electron from the atom. So our first thing that affects ionization energy is the effective nuclear charge. The second factor is, again, the number of shielding electrons. If I have 1 layer of electrons between the valence electron and the nucleus, that's going to have a different energy change than if I have 2 layers of electrons. We call those layers of electrons shielding electrons. And the effect they have on the energy is called the shielding effect. So the number of protons in the nucleus, the number of layers of electrons between the electron we're removing and the nucleus is another one. The third thing is almost a duh, but we're talking about an attraction of a positive nucleus and a negative electron. The farther they are apart, the weaker that is. So a larger radius is going to have a smaller attraction for the electron. And I know the effective nuclear charge affects the radius, but it's an important enough effect that we need to list it as its own factor. And then finally, there's one other factor that has an effect. And this one we can see if we look at nitrogen and oxygen. So if I look at nitrogen in the 2p orbital, I have 3 electrons. For oxygen in the 2p orbital, I have 4 electrons. These electrons have something called an exchange energy, but it's very stable to be in a half-filled orbital. A fully filled orbital is even more stable, okay? But if I have a half-filled orbital, it is relatively stable. So this is a stable configuration, and it takes energy to remove that because it's a stable configuration. Now, even though oxygen has more protons in the nucleus, if I remove this electron, I get something that is more stable. So I am going to have something that we are going to call the sublevel effect. And that is going to be the effect of removing an electron from a filled or half filled orbital. Okay, let's go back to our PowerPoint again. Whoops. All right. Here we see the ionization energies. And as I just showed you, the nitrogen and oxygen that we see right there. Here it is. There's the nitrogen, and here's the oxygen. We see the same thing here with phosphorus and sulfur. So that is something we also see with beryllium and boron. This is something called the sublevel effect. That's why we have those little blips there. They are predictable, and we can expect to be we can expect looking at their orbital diagrams or even recognizing what their orbital diagrams will be like from the electron configuration, we should be able to determine that. Okay, so here's the first ionization of some elements here. Notice again, we see that we expect it to increase as you go to the right, but between beryllium and boron, beryllium has a filled 2s orbital, so it takes more energy to remove that electron than it does for boron, which has one electron, and if I remove it, I have just emptied the 2p orbital, leaving a filled 2s orbital. Okay. All right. Again, I mentioned that successive ionization energies for an element always increase. Okay, so here you can see the first, second, third, fourth, fifth, sixth, etc. ionization energy. Now take a look here. In the case of potassium, between the first and second ionization energy. Now potassium has one electron in the s sublevel, which is a relatively low energy to remove that. Okay, as I remove that electron, the next electron I'm going to remove is not from the 4s, but it is from the 3p. Okay, so it's got a significantly higher effective nuclear charge. In the case of the first electron, the nuclear charge is +1. The effective nuclear charge is +1. For that second electron, the effective nuclear charge is now +9. That's a pretty big increase. I also have a significantly smaller amount of shielding. I have an entire third energy level not shielding the electron from there. So instead of 3 layers of shielding, I now have 2 layers of shielding. The electron is closer to the nucleus, and I am trying to remove an electron from a filled sublevel. Notice that we see large jumps in calcium between the second and third. We see for arsenic, where do we see that big jump? It is between the fifth and the sixth. Well, what does that tell us? If I see where the big jump is, I can tell the number of valence electrons that a particular substance has, even if I don't have the identity of the element. Okay. All right. And we're also going to talk about electron affinity. We're not going to spend a lot of time on electron affinity, but there is an energy change that occurs when we add an electron to an atom. And that is known as the electron affinity. Some places call the electron attachment enthalpy. And this process can be endothermic or exothermic, depending on the element. For the halogens, it's very exothermic. For nitrogen, it's almost impossible to measure the electron affinity energy. Not because we can't get nitrogen to gain an electron, but it's almost impossible to measure the difference between adding the first and adding all 3 electrons to get the nitride ion. Okay. And when we talk about the ionization energy that is forming a cation, the electron affinity is forming an anion. Okay. Generally, electron affinities become more negative across a period. We don't have a true trend up and down in the periodic table. Okay. A couple things that we note. The noble gases have a completely filled shell, and if we add an electron to a higher energy level, it's very difficult to even measure that energy if you can even get it to do that. And we can see some of these others. Okay. So here are some electron affinity values. Notice the nitrogen sitting there with 0, okay? A lot of sources show that the nitrogen does not have a measurable electron affinity. I didn't look up and see exactly what source this was using, but that's been my experience with it. Notice that we have some values that are negative, and we also have some values that are positive, okay? And there are some things that we can take a look at. So just a little review. Here we see the relative shapes of an s, a p, and a d orbital, okay? And I think we are now done with chapter 6, with the exception of working a few problems. So after you've had a chance to take a look at chapter 6, to write a bunch of electron configurations, to compare the ionization energies, I hope you'll have a better understanding of the periodic properties that we call periodicity.